Well, hello. So here's a take a look at what we're doing in 3-5. And we're going to expand some of the exponential work that we've been doing. As you can see right off the bat, our growth and decay looks a little differently now. And that's perfectly okay. In fact, this is the way I initially wanted to teach it when I saw that we had notes that were a little bit different with the time of the event over the cyclic time. It is a little bit different than what I was used to. But this is how I typically have done growth and decay, whereas if it's a growth, we're going to add the rate, usually expressed as a decimal. So you might say, so 25% growth, we could express as 1.25. And if it's a decay, we would subtract. And of course, all these are going to be fairly familiar with you, familiar to you. And here we have continuous. When you have continuous, we're going to use Euler's number right here. That 2.718 blah blah blah, and that's again shows up in nature and in a lot of things, that continuous growth. And for the most part, it's still all the same. Here we're going to toss in the rate and the time right here, and then we have our principal amounts and compound interest for finance reasons. And I've also done these as a Pert problems like this. Okay, so they do come in different forms, and we'll explore a couple of those. But let's go ahead and do our first example. Here's a biology problem where, again, we're going to first break up what's going on here. And we have initial population of a sub 0, so that would be here. And I would go ahead and say we're going to do a growth. So I could have my end population and my initial population being 100. So I'm going to use the 1 plus r. Since we're growing, I know it's going to be a plus, and it's at 25%. So I'm going to convert that to a decimal. All right. And then we're going to look at what's our time frame. Produced at per week. So we're in weeks, so we got to do apples to apples. And there we are, apples, week to week. So I'm just going to call that 6 right there. So this is a pretty simple computation, 1.25 raised to the 6th power, and grabbing my calculator, I get about 381 cells. Okay, so not too bad. That would be a growth. Let's take a look at this one. So here we're now going to look at a finance problem, and I call these my Pert problems. It's going to look a little different what I just showed you, but I have A is equal to PE, because it's continuous, RT. That's the key word. When you see that, think E. All right? So my initial principal, my initial amount, A sub 0, or P as I call it, because I could have said A sub 0 if I wanted to, or A naught. And my rate is here at 8.5, so I'm going to convert that to a decimal of 0.085. Okay? And I have a T for years. So I'm just going to plug it in. So I'm going to have 5,000. So principal is equal to, my amount is equal to 5,000 e to the 0.085 times 13, right? 10, sorry. Okay, so grabbing the calculator, we get about 11,698.23. But it's asking us to compare compounded quarterly. So that is no longer continuous. So the E goes bye-bye, but I'm still going to use the same thing. I'm going to use A is equal to 1 plus R over N times NT. All right? So N is the amount of times that you take a compound. Okay, that's going to be a 4 because you quarterly, 4 times a year. And this T is going to be 10 years. So we're going to have A is equal to 1 plus 0.085 over 4 times 10. What happens here is this is going to, you would think that, oh my goodness, this is a much bigger exponent. But this kind of nullifies it a little bit. It kind of calms it down. So putting all this in the calculator, just the way I see it, comes out to be 11,594.52 cents. right? So you can see a little bit of an advantage of continuous versus compounded quarterly. You're thinking, oh, it's not that much, but it sure enough is to take the family out to hard 8, so I would go for it, okay, if you had a choice between the two. Okie doke, I'm going to get these uploaded and get back to studying for my history class.